めますかね。時間になりましたので。では、so now it's time to start our first colloquium. Today's speaker is Dr. Tetsuya Hashimoto from Taiwan. Hashimoto-san is a CICA fellow at the Institute of Astronomy in National Tsinghua University in Taiwan, working with research interests which include fast radio burst (FRB) and gamma burst in observational astronomy. Today, Hashimoto-san gives a talk. The title is Origin of Fast Radio Bursts and Their Future Applications. So, please, Hashimoto-san, please start your talk.
Okay. Thank you very much for a nice introduction. And also thank you very much for giving me this opportunity to talk about my recent studies. I am Tetsuya Hashimoto from National Tsinghua University in Taiwan. So first of all, let me ask one question. So where do you think the frontier of astronomy is? So, you know, we already detected very distant galaxies. So more or less, we already understand the galaxy evolution and formation scenarios. More or less, we already know the history of the universe. So where is the frontier of astronomy? In my opinion, I think the frontier of astronomy in the next decade is shown in this movie. So that's why I prepared the movie, first of all. This image is showing a typical example of optical image of our sky, which we can see with our eyes. And then, of course, you know, we can also look at the universe in radio wavelengths using radio telescopes. This is a movie. So if you switch to the radio frequency, it is well known that the universe looks very different from optical image. So as you can see, you can find a very difference between optical and radio wavelengths. The most different part is that this radio fireworks, this flashing object, there are so many flashing objects here in radio wavelengths. If you go to the very small, short time scale, there are so many new objects in the universe, which no one noticed before. So this is the frontier of astronomy next decade. I am working on this radio fireworks, this one. This radio fireworks is so-called fast radio burst in astronomy. So today I'm going to talk about origins of fast radio bursts and their future applications. Today's my talk is based on these recent publications in monthly notice. Okay, let me get started. This is outline of my talk today. Let me start with introduction. And I will present our result, which includes the history of the number density of fast radio burst. And I will discuss the future prospects of fast radio burst, especially to be detected with future square kilometer array, which is the largest radio telescope in the future. And also I will talk about the applications of fast radio burst. This is a new method to reveal the cosmically ionization history using future fast radio burst. And also let me talk about testing general relativity using fast radio burst. And then let me conclude in the end in my talk. Okay. So let me start with introduction. So what is fast radio burst? Fast radio burst, FRB, is an extragalactic burst in radio frequency. So this image is, okay, so let me show pointer here, this one. So this image is showing an imaginary picture of fast radio burst, which is coming from extragalaxy here. So this fast radio burst is kind of radio pulse. This is sudden brightening of the object. And then this object immediately disappears, becomes faint, like this. This is like a radio pulse here. Then actually this fast radio burst is very bright, which is comparable to the Jansky level. This Jansky is very bright in astronomy usually. And then one unique point of this fast radio burst is its duration. The time, duration of this pulse. This duration pulse is very short, which is a millisecond level. Because this millisecond time scale is very new in astronomy, Actually, no one noticed this object before. Just recently, astronomers started to find this mysterious radio burst. The many astronomers are excited in first radio burst now. Indeed, more than 10 Nature papers have been published about the first radio burst since 2019. Currently, this is Chinese biggest radio telescope at the moment. First, and this is the Canadian radio telescope CHIME. This is also Radian ASCAP and PARCS. These radio telescopes are actively finding first radio burst now. Observationally, there are two different types of first radio bursts. One is non-repeating FRBs, another is repeating FRBs. Here, there must be the astrophysical source which is emitting this mysterious radio burst. If you detect only one-time radio burst from the same astrophysical source, you say this is non-repeating FRBs. But somehow, there is a repeating FRBs too. If you detect multiple radio bursts from the same astrophysical source, then this is repeating FRBs. If you collect currently detectable first radio bursts, more than 1,000 FRBs are happening every day on sky. This number is very large in astronomy. We know that there are so many this mysterious radio bursts in the universe, but the problem is that we don't know their origins. Their origins are still unknown. So revealing this origin of first radio burst is one of the central forces in astronomy now. Okay. So this is the example of detection rate of first radio burst as a function of time. So as you may know, the detection rate of first radio burst is rapidly increasing recently. Since the first discovery of the first radio burst, this detection rate is increasing. Currently, publicly available FRBs are about 100 in total. However, recently the Canadian radio telescope, this is CHIME. This CHIME radio telescope detected so many FRBs recently, which is more than 1,000. If new FRBs will be released in this year. So because this 1,000 is one order of magnitude larger than the currently available FRB sample, so therefore many astronomers are excited in first radio burst now. And here, let me introduce unique observable, what we can observe from first radio burst. Let me introduce unique observable of first radio burst. This is a typical example of FRB detection, which is observed frequency in y-axis as a function of observed time. And then, as you can see, there is a straight line here. This is tilt line here. This is a typical example of FRB detection. Actually, we see a tilt line here. This is because the speed of light will change when this radio emission goes through the ionized material in intergalactic space due to the plasma effect. Therefore, we expect different arrival time depending on different frequencies. Therefore, we see time delay between different frequencies. So this is so-called, this time delay is between different frequencies is so-called dispersion measure. So this dispersion measure is very unique in FRBs. Then we can use this dispersion measure for indicator of distance. So let me explain these things in next slide. So as you may know, our universe is more or less on average ionized. So universe, intergalactic space of the universe is occupied by ionized materials. So this is a schematic artistic image of intergalactic medium. This here corresponds to distant universe, and then this is nearby universe. Then our observer is standing at here, let us show 0. So if first radio burst, FRB happens at very distant universe, for example here, you have more amount of ionized materials in between the first radio burst and observer. then you have more amount of ionized material. Therefore, you expect a longer time delay between different frequencies. Then you have larger value of dispersion measure. In contrast, if FRB happens at a nearby universe, for example here, you have less amount of ionized materials in between FRB and observer. Therefore, you expect shorter time delay and smaller value of dispersion measure. So in this sense, by measuring this dispersion measure, I mean time delay between different frequencies, you can estimate the distance to individual FRBs. So this is a unique point of FRBs. When we detect FRBs, automatically we can estimate the individual distance. And then this is about dispersion measure. And then other things are actually easy. So the second one is pulse duration. We can, of course, we can measure how long is this pulse from observations. And fluence is how bright is this pulse. And then repetition is whether or not you detect multiple radio bursts from the same source or not. Basically, these four things are unique observable typical observable of first radio burst. The point is that we can measure the distance of first radio burst using dispersion measure. Okay. So this is a kind of basic knowledge of observations of first radio burst. In terms of theories, FRB theories are kind of in a chaos situation. Actually, more than 50 theories of first radio burst origins have been proposed. So here I selected the possible candidates of FRB progenitors, so which includes white dwarf, neutron star, and stellar mass black hole. This is stellar mass black hole, and magnetar, young pulsar, supermassive black hole, and supernova remnant. Basically, astronomers believe that the origin of first radio burst should be the astrophysical sources. But however, interestingly, there is one theory that aliens in the universe may produce this kind of first radio burst. This is one theory. Anyway, revealing this origin of first radio burst is most important tasks in astronomy now. And then in FRB research, we had a very big news recently. Recently, the one galactic repeating FRB was confirmed to be associated with a galactic magnetar, this one. Thanks to the CHIME and other radio telescopes. And thanks to these great works, we know that at least one repeating FRB originated from a magnetar. But however, the problem here is that we only know about one confirmed case out of the more than 100 currently available first radio bursts. We don't know at all about the remaining more than 99% of extragalactic first radio bursts. So this is the problem. And also, this problem is due to the previous method to try to reveal the origin of first radio burst. In previous research, they tried to localize first radio burst positions in the sky in order to reveal their origins. I mean, localize means that you want to measure the accurate position of first radio burst in the sky. If once you know the accurate position of first radio burst, you can identify the host galaxy. I mean, the galaxy hosting first radio burst. Therefore, you can't get any hint to reveal the origin of first radio burst from localization. This is one of the promising ways. Actually, indeed, we got the one confirmed case from this method. However, observationally, this localization is not really easy. Therefore, we have only one confirmed case. This localization didn't very well because of the observational difficulty. Therefore, in our research, we changed our mind, we changed the point of view, and then we uniquely focused on the history of the number density of first radio bursts. in order to reveal the constraint, the origin of fast-related burst. This is our study. Okay, let me explain how it works. Here I again show the possible candidates of FRB progenitors. Then roughly speaking, we can divide FRB origins into two categories. One is old object, another is young object. Old object is the old object with very long lifetimes, which is a giga-year time scale. They can survive almost forever, say giga-year time scale. The point here is that the number density of this old object should be proportional to the cosmic stellar mass density, because stellar mass in the universe is dominated by old objects in general. Therefore, by counting this cosmic stellar mass density, we can estimate the number density of this old object, which is actually already measured from galaxy observations. Then this number density of old object shows a nearly constant trend from a present universe to the past universe. I mean, past means, in my talk, past means redshift up to 1.5 or 2, something like that. Therefore, if FRB originates from this old object, the number density of FRBs should also follow this nearly constant trend from present to the past universe. This is our logic. In contrast, the number density of young objects should be proportional to the activity of the galaxies, either star-forming activities or supermassive black hole activities, because these young progenitors are remnant of activity of galaxies. Then this number density of young object is also already measured from the galaxy observations, which shows increasing trend from the present to past universe. Therefore, if FRB originates from these young objects, we expect that the number density of fast-related bursts should also follow this increasing trend toward the past universe. In this sense, by revealing the number density evolution or number density history of the fast-related burst, whether or not constant or increasing toward the past universe, we can strongly constrain the origin of fast-related burst. This is our unique idea. And then here I show that already measured the expected number density of old objects and young objects. Let me say white dwarf et al. For old object here, which is shown by yellow line here. This is already measured from galaxy observations. And the number density of young object, let me say Magneta et al., etc. in my talk. The number density of Magneta, etc. is also already measured from galaxy observations, which shows increasing trends, which is shown by blue line here. So then we, for the first time, revealed that the number density evolution, history of the number density of fast-related bursts. Here I show the number density of non-repeating FRBs, which are shown by red stars here as a function of look-back time of the universe here. Sorry. We, for the first time, found that the number density of non-repeating FRBs are all nearly constant over the past 10 giga years. This nearly constant trend is indeed consistent with the number density, history of the number density of white dwarf, etc. here, which are shown by yellow line here. So in contrast to this, the number density of Magneta, etc., blue line, is not consistent with the nearly constant trend of the number density of non-repeating FRBs. So this our result clearly indicates that non-repeating FRBs likely originate from old objects such as white dwarf. And then, okay, this is white dwarf. And then let me go back to the expectation. This is the expected number density evolution for young object and old object again. And then we also, for the first time, show the number density, history of the number density of repeating FRBs, which are shown by purple stars here. So as you can see, we found that the number density of repeating FRBs actually increased toward the past universe over the 10 giga-year. So this increasing trend is actually consistent with the increasing trend of magnetar, etc., and which is inconsistent with the white dwarf, etc. here. So this result clearly indicates that repeating FRBs likely originate from young objects such as a magnetar. So let me summarize this point. Okay, magnetar. Let me summarize this point. So observationally, there are two different types of first-order bursts, non-repeating and repeating FRBs. The revealing the origin of first-order burst is the one of the central forces in astronomy now. So by using our unique statistical approach, we found that the number density of non-repeating FRBs are nearly constant over the past 10 giga-years. This nearly constant trend is actually consistent with the number density evolution of all the objects, which includes white dwarf and neutron star and stellar mass black holes. So in contrast to this, we also found that number density of repeating FRBs increased toward the past universe. Here, increase. This increasing trend is consistent with the activity of the galaxies, either star-forming activity or supermassive black hole activities. Therefore, repeating FRBs likely originate from young objects, which include magnetar, young pulsar, active supermassive black hole, or supernova remnant. So let me emphasize that I mentioned that there is a confirmed case for repeating FRBs, which is indeed associated with magnetar. Therefore, our statistical approach is actually consistent with one confirmed case. So this is the first time that the origin of first-order bursts strongly constrained. Therefore, this result was selected for press release in Astronomical Society of Japan just last month. And then the result appeared in newspaper, both in Taiwan and Japan. So this is about origins of first-order bursts. And then in the remaining time, let me talk about the future of FRBs and applications of FRBs in different fields. Okay. So let me talk about the future of first-order bursts. Especially let me focus on the future square kilometer array, which is the largest radio telescope. So here I summarize the key sciences which are related to the FRBs in future. So first of all, revealing the origin of first-order bursts. This is still important, very important. And then the first-order burst is also expected to allow us to address the time variability of the dark energy. And also FRB is expected to be useful to reveal the cosmic reionization history. So I will talk about this later. And also FRB is very sensitive to the missing baryon problem. The missing baryon problem is the problem that we can only detect the tiny part of expected amount of baryon in the universe from observations. There must be missing parts. Then people expect that this missing part of baryon should be in intergalactic space. But observationally, it is in general, it is not easy to trace the material in intergalactic space. Therefore, this is a missing baryon problem. But first-order burst is very sensitive to materials in intergalactic space because they have unique observable or dispersion measure. And also, first radio burst is very useful to test general relativity. Let me talk about this later too. So anyway, what I want to say here is that all of these topics are very important, in, not only in astronomy, but also in physics. However, currently we have only 100 FRBs. So this number, 100 FRBs, is not enough to address these key sciences in physics and astronomy. Therefore, next key question is how many FRBs will be detected in near future? So in order to answer this key question, I published this paper. This paper was also featured by Astrobytes. So if you want to know the details of this paper, you can go to just Astrobytes, which is summarized in easy language. So as you may know, that in future, we will have the square kilometer array, which is SKA. Then SKA will start science operation in 2020s in South Africa and Australia. And okay, so as you know, so China is a part of this big international collaboration. So what's nice in SKA? SKA is very good in finding fast radio burst. Let me briefly explain. So this is the sensitivity of radio telescopes as a function of field of view of telescopes. And then Parkes radio telescope, this is a radio telescope which is currently working to detect fast radio burst. Comparing to this Parkes radio telescopes, the SKA, actually this is full science operation phase, say phase 2 of SKA, will have the two order of magnitude better field of view and also 2 order of magnitude better sensitivity. Therefore, SK is much better than currently working radio telescopes in terms of finding fast radio burst. So we expect so many fast radio bursts to be detected with SKA. So let me predict quantitatively how many FRBs will be detected. So by using our number density calculation measured from local universe, and then I predict how many FRBs to be detected with SKA, which is shown in y-axis. This is the number of FRBs in SKA era. Actually, this is cumulative number in log scale as a function of redshift here. Then, as I said, there are two different populations of FRBs. One is non-repeating FRBs, another is repeating FRBs. They are shown by blue and red respectively. And then this is cumulative number. Therefore, the expected number is always decreased towards this higher redshift. Anyway, so as you can see, there is a range here. Okay, for the first of all, in terms of number density, actually expected FRBs is dominated by non-repeating FRBs. This is because the number density of non-repeating FRB is actually much larger than repeating FRBs. And then in my prediction, there is a range in y-axis in number. This range corresponds to the different assumptions on redshift evolution of FRB luminosity functions, which is proportional to either cosmic star formation rate density or cosmic stellar mass density evolutions. So anyway, so I assumed two extreme cases here. Therefore, in reality, real number should be is expected to be located in between. Anyway, the point here is that we expect 10 to the 5 to 10 to the 6 fast radio bursts to be detected with the SKA phase 2 in total. This is per year. Even at very high redshift, at the cosmic reionization epoch, which is at redshift higher than 6, we expect 10 to the 2 to the 10 to the 4 fast radio bursts in the SKA era. These numbers are much larger than the currently available FRB datasets. Therefore, I believe that this number is large enough to address the key sciences that I listed in the previous slide. So Especially in the next slides, let me focus on the cosmic reionization to be revealed by these future FRBs. In next slides. So let me talk about cosmic reionization. So one sentence summary of this part is we propose a new method to reveal the cosmic reionization using future first order bursts to be detected with the SKA. Okay. So again, this is an artistic image of intergalactic medium, which is actually related to the cosmic reionization history. So this cosmic reionization history is one of the biggest phase transitions of the universe from neutral phase to ionized phase. And then this reionization is supposed to be related to the first formation of stars and galaxies. Therefore, revealing this cosmic reionization history is the frontier of galactic astronomy now. So many people want to understand this cosmic reionization history, actually as a function of redshift. Okay, and then observationally, there are two complementary ways to investigate this cosmic reionization histories. One is using neutral hydrogen, tracing neutral hydrogen, which uses quasar spectrum or 21 centimeter emission or absorption lines from atomic hydrogen. And then another way is that directly tracing the ionized material in intergalactic space using cosmic micro background CMB or first radio burst FRBs. So because first radio burst FRB is categorized in this category, ionized material category. So in my talk, let me compare CMB and FRB methods. So first of all, let me briefly explain how CMB can constrain this cosmic reionization history in next slides. Okay, this is again cosmic reionization history. So as you know, this cosmic microwave background CMB propagates from redshift 1100 to all the way to the redshift 0 here. And then during this propagation, CMB will experience the Thomson scattering due to the free electrons in intergalactic space. Therefore, by observing this CMB, we can actually calculate the optical depth of this Thomson scattering. Then this optical depth of Thomson scattering, let me say tau CMB, this times CMB is actually integration of electron density in intergalactic space over the redshift from 0 to 1100. Therefore, this tau CMB is an indicator of the amount of ionized materials in the universe. So, for example, if this reionization happens at very distant universe, for example, around here, if reionization happens here, after this epoch, we see the ionized materials in intergalactic space. Therefore, if reionization happens at very early epoch, we expect more amount of ionized materials in between the reionization and observer here. Therefore, we expect a larger value of optical depth tau in this case. In contrast, if reionization happens at very nearby universe, we have less amount of ionized materials in between reionization and observer here. Therefore, it expects very small value of optical depth tau. So in this sense, by measuring this tau CMB from CMB observations, we can roughly constrain the averaged epoch of cosmic reionization, which is maybe here, maybe here, maybe here, something like this. This is how CMB works when we constrain the cosmic reionization history. The problem here is that the CMB using optical depth tau, CMB is basically sensitive to only averaged epoch of reionization. So CMB is not really sensitive to the detailed structure of cosmic reionization histories as a function of redshift, which is actually what we really want to understand. So CMB is not really useful to investigate the details of reionization histories. This is because optical depth tau is already integrated over redshift 0 to 1100. This is already integrated over redshift range. Therefore, this is not really sensitive. Then in order to overcome this problem, we propose a new method to reveal the cosmic reionization as a function of redshift using feature first order burst. This as a function of redshift, this part is the advantage of our FRB method. Let me explain. So as I said, this is a schematic diagram to summarize the actual situation of first order burst. And then, as I said, we expect that the many first order bursts are supposed to be happened at distant universe at different redshifts. And then for each FRB, we can measure the dispersion measures. And then actually this dispersion measure is very similar parameter to the optical depth tau CMB. This dispersion measure is also integration of electron density in intergalactic space over redshift 0 to the each redshift of each first order burst. This is a very similar parameter to optical depth tau. But different point is that we see many FRBs at different redshifts. Therefore, we can measure this dispersion measure as a function of redshift here. This point is very different from CMB situation. Actually, as you can see, we see that so many red horizontal lines here in FRB case, while in CMB case, we saw only one single line, single white line here. This is a different point. And then in our paper, we propose to differentiate this dispersion measure against redshift. So as you can see, if you differentiate this dispersion measure against redshift, you can directly calculate this electron density or ionization fraction in intergalactic medium. Therefore, from FRB observations, once we measure this DDM-DZ, we can directly calculate the ionization fraction of the intergalactic medium as a function of redshift using first order burst. This is the advantage of first order burst over CMB. So in next slides, let me demonstrate how much we can constrain the reionization histories using future first order burst. So for this demonstration purpose, we assumed 3 different cosmic reionization histories, which are shown by different 3 colors in this diagram. Y-axis is an ionization fraction of intergalactic medium as a function of redshift. So here, different color corresponds to different histories of cosmic reionization. Then point here is that all of these reionization histories show the exactly same optical depth tau value. Therefore, using optical depth tau CMB, CMB cannot distinguish between these 3 different reionization histories. But I will say that first order burst can differentiate between different reionization histories shown in here. So by using these different reionization histories and also expected numbers of FRBs in the SK error, which I showed before, using these 2 things, I constructed mock FRB data, which is supposed to be observed in near future in the SKA era. So this mock data is shown in different panels here. This is y-axis is dispersion measure as a function of redshift. different panels correspond to different assumptions on the cosmic reionization histories. And then in each panel, the one colored dot corresponds to one mock data of FRB. And then mean of mock data are shown by black squares in each panel. Okay? So then, as I said, DDMDZ, this parameter is really important because this is directly proportional to the ionization fraction of the intergalactic medium. Then in this parameter space, dispersion measure as a function of redshift. So, this DDMDZ is actually slope of mean data points. So let's assume that in future, we will observe this kind of mock data using SKA. Then using this observed data, we can measure DDMDZ, which is slope in this diagram. Then by measuring DDMDZ, we can directly calculate ionization fraction as a function of redshift for each mock data. Then using this method, we reconstructed the ionization fraction of the intergalactic medium as a function of redshift, which is shown in this figure. This is ionization fraction as a function of redshift. Different panels correspond to different ionization histories. And then originally assumed reionization histories are shown by solid line here. This is original assumption. And then our reconstructed ionization fraction are shown by filled or open circles here. And as you can see, by using future mock FRB data and our method, DDMDZ method, we can consistently reconstruct ionization fraction as a function of redshift. So there are 2 points in this diagram. One is that, as I said, using tau CMB cannot distinguish between these 3 different reionization histories. However, as you can see, FRB can differentiate between these 3. Especially, for example, this double reionization feature can be reproduced by using our methods and future FRBs. And the second point is that FRBs allow us to measure the reionization history as it is. This is because when we reconstruct this ionization fraction of intergalactic medium, we do not assume any functional shape of reionization histories. Therefore, we can actually measure reionization history as it is without any functional shape assumptions. So this figure clearly indicates the feasibility and capabilities of future FRBs and our method. So FRB will be really useful to reveal the reionization history in the future. Okay. And then in the remaining time, let me talk about our newest results, which was submitted to monthly notice recently. Let me talk about the general relativity in the remaining time. So FRB is useful to test general relativity. Okay, let me briefly summarize the history of the general relativity here. This is a very simplified version. So as you know, in the past, Isaac Newton proposed the Newtonian mechanics, which is great, more or less the Newtonian mechanics works in many cases. However, Michelson-Morley experiment revealed that the speed of light is always constant in the vacuum. So this experimental fact cannot be explained by Newtonian mechanics. Then these things initiated the hint of general relativity, which was proposed by Albert Einstein. Then for now, many physicists try to find new theory which is beyond the general relativity. Therefore, I believe that it is a good time to go back to the testing the speed of light again. Actually, FRB is very useful to accurately test this speed of light, which may allow us to find something hint to find a new theory beyond general relativity. Okay. Especially in my study, let me focus on so-called Einstein's weak equivalence principle, WEP. So WEP is a statement that the speed of light is always same for different frequencies under gravitational potential, which sounds reasonable. Okay, so our Earth is located here within Milky Way here. This Milky Way is surrounded by other external galaxies, which creates the galaxy clusters. And then these galaxies create the huge gravitational potential around the Earth. And then there is an astrophysical source, which is actually in this case FRB, which is emitting photons at different frequencies. Say photon 1 at frequency 1 with speed of light c1. And then photon 2 with frequency 2 with speed of light of c2. Then this WEP is assuming that C1 equals C2, exactly equals C2 under the gravitational potential. So this sounds reasonable. But I would say that it is always important to accurately test this general relativity, because this may provide us a hint to find a new theory in future. Then if speed of light is different between different photons here, different frequencies, we expect the time lag between the photon 1 and photon 2, because their speed of light is different. Okay. So actually, first radio burst is very useful to test this WEP violation of WEP. This is because this first radio burst actually traveled the cosmological distances, very long distances. And eventually we measured a very short time scale, which is milliseconds eventually. Therefore, this first radio burst is very sensitive to the very slight difference of speed of light between different frequencies. And then if this WEP is violated, we expect a time lag between different frequencies. Okay. Then in observations, actually we see the time lag between different frequencies actually when we detect the first radio burst. If you remember, this is the detection of first radio burst, the observed frequency as a function of observed time. Actually, arrival time is different for different frequencies. Okay, but this time lag between different frequencies is not because of the WEP violation. This is totally explained, can be explained by plasma effects, which is dispersion measure. Because when, as I said, when radio emission goes through the ionized materials, speed of light indeed change. Then this time lag should be proportional to the inverse square of observed frequency, if this is because of the plasma effect. Then actually, observationally, this curve is accurately fitted, can be fitted by using this inverse square law. Therefore, in order to explain this time lag between different frequencies of FRBs, actually we don't need to introduce WEP violation. Everything can be explained by plasma effect only. But in other words, that means if WEP is violated, that signature, this sign, have to be within the observational uncertainty of FRB detection. Otherwise, we should be able to find the deviation from this inverse square law. But actually, in reality, from observation, we don't see any deviation. That means this WEP violation have to be smaller than observational uncertainty. Therefore, we don't see clear feature. So in this sense, actually, this observational uncertainty of FRBs can place an upper limit on this WEP violation, which is actually very accurate. So when people parameterize this WEP violation, people use delta gamma parameter, which is defined as gamma 1 minus gamma 2 for photon 1 and photon 2, respectively. And then this gamma 1 should be have to be exactly equal 1 if WEP is not violated. This is a GR case. If GR case, W1 is exactly same as gamma 1 is exactly same as gamma 2, and then therefore delta gamma have to be exactly 0 if WEP is not violated. In other words, if WEP is violated, we expect a non-zero value of this delta gamma parameter. And then actually what we can do is we can constrain the upper limit on this delta gamma parameter, which is shown in y-axis here in log scale as a function of frequency, observed frequency. And then previous constraints from previous works are shown by black markers in this diagram. And then our method, which uses the observational uncertainty of FRB detection, actually observational uncertainty of dispersion measure, our constraints are shown by red circle here. Then one red circle corresponds to one FRB. And then if you focus on the most accurate one, I mean, this is the upper limit, therefore the smaller is better. If you look at the smallest value from our research, which is actually more than 1 order of magnitude better than previous works. So even though we do not detect any clear feature, any clear evidence of WEP violation, but by using FRBs, we actually achieve the most accurate test of general relativity than ever, which is 1 order of magnitude better than previous works. Therefore, I would say that this kind of test is very important because which may provide us a hint to find a new theory in future beyond general relativity. Okay, so maybe I spend a lot of time. So let me conclude my talk today. Observationally, there are 2 different types of FRBs, non-repeating FRBs and repeating FRBs. And then we, for the first time, found that the history of the number density of these 2 different populations shows very different. Therefore, these non-repeating FRBs are likely originate from old objects such as white dwarf, neutron star, and stellar mass black holes. And repeating FRBs likely originate from young objects, for example, magnetar, young pulsar, supermassive black hole, or supernova remnant. This is about the origin of FRBs. And in near future, SK will detect 10 to the 5 to 10 to the 6 FRBs per year. Then this number is much, much larger than the current available sample. Therefore, I believe that this number is large enough to address the cosmic reionization history in the near future. And also, first radio burst is very useful to test the general relativity, which may provide us a hint to find a new theory in future. Okay, I stop here. Thank you very much.
Okay, thank you for a good talk, Hashimoto-san. So now it's time to discussion. Does anyone have a question or comment?
I have some questions. Excuse me. Okay. First, is it still a very strong evidence for the first work, even when you consider about such as the completeness and the classification of the 2 types of FRB of the observation? I mean, is it still a strong evidence?
Okay, so I believe that in my analysis about the completeness, I believe that I actually, in my paper, I unified the definition of the detection threshold. And then I actually conservatively used only bright FRBs. Therefore, I believe that completeness doesn't affect very much in my analysis, result. And also, in terms of classification between non-repeating and repeating FRBs, this is also a very good point. As you know, so actually this is just an observational definition. Therefore, as time goes by, it may be possible that non-repeating FRB will become repeating FRB because we may detect the second burst, then non-repeating FRB will change to repeating FRBs. In this sense, actually, this is just an observational definition. Then this definition will change as a function of time. This is true. But my personal preference is that the number density between repeating and non-repeating FRBs at the moment is actually very different. Sorry, I don't have, sorry, let me show. Actually, I calculate the luminosity function for repeating and repeating FRBs. And this one, for example, this is a luminosity function of repeating FRB and non-repeating FRBs. And then y-axis is a number density of FRBs as a function of luminosity. So for example, at a fixed luminosity range, for example here, the number density of repeating FRB is much, much smaller than repeating FRBs, according to my luminosity function. This difference is about a 2-order magnitude difference. And then my personal opinion is that, of course, this number classification between non-repeating and repeating may change in future, but at the moment, number density is very different, 2-order magnitude difference. Then I don't think the repeating FRB is increasing to overcome this difference. So therefore, as far as I am focused on these several years, I don't see this repeating FRBs, number density of repeating FRBs change significantly. Therefore, in this sense, more or less, I think our analysis is not really affected by this classification problem.
Okay, thanks. Maybe another question is the second part about the reionization history. You test 3 different models. So can you explain more details about the model, especially for the double, or the different of model is due to astrophysics or due to cosmology?
Okay.
This is my
So
question.
Actually,
okay.
Thank you very much. That's also a very good point that I didn't explain at all. Thank you very much. Actually, I'm not really familiar with this part, but okay. First of all, this double reionization scenario, red one, is, I would say this is not mainstream of the theoretical mainstream, but some paper expect this double reionization feature because they say that there is a POP3 star, and a POP3 star ionizes the universe first. And then this is because of the POP3 stars. And then after that, normal galaxies reionize the universe again. This is responsible for the normal galaxies, star-forming galaxies. Therefore, in some model, they expect this double reionization feature. This may be minor theory, but the point here is that even if there is this kind of substructure of reionization histories, we can actually measure using fast order burst. And then this is about double reionization. And then as far as I know, this asymmetric green one, this is motivated by simulation, I think, simulation of galaxy, cosmological galaxy formation and evolution scenario. If you do galaxy simulations, this reionization history can be well fitted by using this asymmetric structure. This is for the simulation. And then blue one, about blue one, I don't think there is a physics behind the blue one. This is just assumption. This is conventionally used for the CMB people because CMB is not really sensitive to different these structures. Therefore, they just simply assume this instantaneous this shape. Actually, this is a hyperbolic tangent shape.
Okay, thanks. Thanks very much.
Does anyone have a question? Okay, so I have a question about statistics of FRB. So at first part, you analyzed the progenitor of FRB repeating or non-repeating based on number density. I forget, but my question is that currently the number of FRB is about around 100. The statistics is enough for your analysis. This is my question.
Okay, thank you very much. That is very important. Okay, so yeah, the statistics is not enough actually. And then we definitely need new data, actually, which will be provided by CHIME, actually. For my purpose, actually, this number density purpose, actually, I wanted to use the homogeneous sample, which are taken by only single telescope. If I combine between different telescopes, then we may have unknown systematics between different telescopes. Therefore, I limited my sample to the homogeneous sample, then which significantly reduced the number of sample actually. And then I used less than 100 here to calculate the number density evolution. And then definitely, you are right. We definitely need more number of FRBs, especially more number of homogeneous FRB sample is very important to conclude this point. And then CHIME, as I said, CHIME will provide this homogeneous sample, which include hopefully more than 100, more than several hundred or thousands. And then if we use new CHIME data, which is not yet published, but if we use this new CHIME data, I think we will be able to conclude this point soon. So my answer is that this result may change. Yes.
No.
Because of the
but you only use 100 FRBs, but the error bar is very small. So yeah, so this is one.
That is because log scale, I think. I believe I correctly included all of the uncertainties when I calculate density. Of course, I also included the Poisson uncertainty, and also I included the luminosity function uncertainty, blah, blah, blah. But yeah, this is log scale, so.
I see. Okay, thank you.
Hello. I also have a question about this plot. So
Okay.
can you hear me? Okay.
Yes.
So here for the non-repeaters, you actually show that the data point follow this yellow line. But for the repeating FRB, let's follow closely to the purple line. So it seems here that the purple line is above the yellow line when you go to a high resolution, right?
Yes.
Okay, but then in your luminosity function plots, it's actually the repeating FRB, the luminosity function is much lower.
Okay. Sorry, maybe I didn't explain details of this figure. Actually, what we want to investigate is the number density evolution. This is actually relative number density evolution. Then, okay, so this absolute number is true for this red star here, but this number density of magnetar, etc., and white dwarf, etc., here, these two lines, actually, I can scale arbitrarily because I'm just checking whether or not the number density is increased toward this past universe or constant. Therefore, actually there is a normalization, between these. So I think that's the reason. For example, if you look at the red one here, this is 4 in y-axis in log scale. And then repeating one is actually less than 4 in this diagram. But these lines I arbitrarily scaled. But this observed, calculated number density, the stars, actually this absolute number is this one. So actually this is consistent with our luminosity function calculation.
Okay, so in other words, those 2 lines actually you can shift as you keep the trend.
Exactly.
Okay, thank you.
Does anyone have a question? Okay, it seems no question. So that's all for today. Thank you for great talk, Hashimoto-san. Thank you.
Thank you very much. 谢谢. Okay, so bye bye.
バイ。後で動画の方は送りますので。
ありがとうございます。はい、じゃあ、
はい、
ありがとうございました。お疲れ様です。
はい、ありがとうございました。
はい、ありがとうございます。
お疲れ様です。
失礼します。
ありがとうございます。